Hey everyone, welcome back to the YouTube channel. I am Xavier Smith, and today I'm going to go over a more complicated related rates problem. This is just one problem in the video, so let's get right into it. Okay, a conical cup 30 centimeters across and 5 centimeters deep is being filled with water at a rate of 2 centimeters cubed per second. What is the rate of the height when the water is 3 centimeters deep? So for our little graph here, this is 30 centimeters across, meaning diameter is 30 centimeters, so I just put radius as 15, and it's 5 centimeters deep. And then we can't graph that 2 centimeters cubed is what is being filled. But then we're saying, okay, this is the water level here. This would be the height, which would be like 3 inches. And then here would just be the radius of the water. Just we might be able to use that calculation later. Okay, so we are given that a volume of the cone is V equals 1/3 pi r squared times height, right? So if we use this equation and take the derivative, which what we can do right now, which would be dv over dt equals 2/3 pi r, we're going to treat this right here as a product rule, pi r dr over dt plus 1/3 pi r squared times dh over dt. And we just did that because we're going to say 1/3 pi r squared is one variable multiplied by another variable. And we just did product rule, which is f prime of x times g of x plus f of x times g prime of x. So we did all that. And again, we just took the derivative of the radius in relation to time, derivative of volume in relation to time, derivative of height in relation to time. Okay, so what do we need here? Well, we need dv over dt, which we have as 2 centimeters cubed per second, because that's the rate that the volume is changing per second. Okay, now we need the radius. We're not given the radius, right? We have nothing telling us what the radius is right here for the water. And we also have nothing saying what the change, like the rate of change of the radius is. So we can't do that. And then radius squared, again, we don't have the radius. And dh over dt is what we're solving for. So we really don't have anything here. Like, we cannot solve this equation. There's 3 unknowns, so we just physically cannot solve it. So we say, okay, looking back at the base equation, what do we have? And like, what do we need to have in our final equation? Well, here clearly we are solving for the rate of the height that's changing. So we need an h because we're given height. So we're going to say like we need like volume, right? So we need v, and then we're given height. So we need height, and we're finding for dh over dt, the rate the height is changing over time. So dh over dt, which will come from derivatives. So it looks like we're going to have this volume equation here, but without the radius. Everything in this problem, like all this radius stuff, we just can't solve. So if we can somehow get rid of the radius in this volume problem, then take the derivative, we will have a problem with the isolated v equals h and dh over dt. Okay, so let's try to solve for that. Trying to get rid of the radius here, we're going to try to find out what is r equal to. Well, if you look at this right here is like a flat line, this is a flat line, and then this should be a straight line right down the middle of the cone. So these would really be 90-degree angles. Okay, so having the same side, same angle, another same angle here, this is really a look at similar triangles. So if we like pull these triangles out, we're going to have this. Oh, that does not look good. This, H, R, this whole thing is 5, and then this is 15. So there's a lot of ways you can use similar triangles here, but I'm going to say like H is to R as 5 is to 15. Because like these are similar triangles because they have the same 2 angles, same sides. They have like the same everything. I'm not too good at my geometry, but I know these are similar like triangles by just looking at them. So like H is to R in this triangle. Like the side is to this side is to this side as 5 is to 15. This side is to this side. So h is to r as 5 is to 15. And then we can solve for r here. We can cross multiply and get 5r equals 15h, and r equals 15h over 5, which will be r equals 3h. Okay, now we have r equals 3h. We go back to this volume equation and just get rid of r. So v equals 1/3 times pi 3h squared times h. Okay, v equals, like, we're just going to simplify that to pi over 3 times 9h squared times h. 9h squared times h. That'll cancel. That'll become a 3h, because that'll be 9 pi over 3 is just the same thing as 3 pi. And then these will multiply. H squared times h is really h cubed. So we get v equals 3 pi h cubed. Okay, now that we have the base equation with just h in volume, we are going to take the derivative. So now we get dv over dt equals, take the derivative of this, would be 9 pi h squared dh over dt. So 9 pi h squared dh over dt. Just using the power rule here, saying 3 pi is the coefficient. Okay, so now we have everything we need. We're solving for dh over dt. We have height and we have dv over dt. So dv over dt is 2 equals 9 pi times height is 3 centimeters. The water is 3 centimeters deep. So 3 centimeters squared times dh over dt, which is what we're solving for. So this would really be 9. And then this 9 pi times 9 would be 81. So 2 equals 81 pi dh over dt. And then we go dh over dt. You divide both sides by 81 pi equals 2 over 81 pi. And then the rate that the height is changing, height would just be a singular, like, centimeters. So this would be centimeters per second. So cm per second. And then you could always simplify that in your calculator if you would like to. Okay, well, that is our math problem right there. Let me know if I did anything wrong. Of course, I'm fallible. I can do something wrong. But this is really the basic idea of the problem. And the main problem was that in the equation we knew in our heads, we had a variable that we couldn't solve for. We couldn't solve for radius. And by having radius, it gave us, like, taking the derivative of radius in relation to time gave us radius and dr over dt, which we can't solve for either of them because we're not given. So again, you just have to find out how to get rid of the radius in this problem. And here in the cone problem, we just had similar triangles, and we just solve for r in relation to, like, h here, and then just plug back in. Then you take the derivative, right? So don't take the derivative here and then try to plug in things. It's not going to work. Just, like, change the base equation and then take the derivative and then plug in everything and solve. And you should be good. I hope everyone enjoyed, and I'll see you in the next one.